we are going to look at an example soon. I'm just going to quickly sort of walk through what are the parts of this example that we need to keep in mind. We are going to be modifying our RTL corresponding to the smart timer such that it can actually generate an interrupt, okay, and that interrupt is basically going to be on the counter wraparound, that is when it reaches the entire period and wraps around over there, that is the overflow, right, it causes the interrupt signal to get set. And the counter by itself continues counting, but what can be done in that case is that since it generates the interrupt, what we say is that that goes back, wakes up the CPU then comes back and needs to basically clear the interrupt, okay. So the counter wrap is going to set the status.wrap bit, which we will see inside the RTL. That also asserts the IRQ out signal, which is then going to remain high. Remember what we said about a level triggered interrupt. That IRQ out signal is what we will connect to the GIC as our interrupt signal, right. That interrupt in turn will cause the software handler to get triggered. The handler will read the status, see that wrap is equal to 1, write 1 to the status.wrap register, which is basically a write 1 to clear kind of register, and clear it. And therefore, every time that we get the interrupt, it will basically go clear this bit and say, okay, now the IRQ out goes back to 0, okay. So the IRQ, in other words, implemented in this way is going to stay high until it's acknowledged, and we will look at both how the RTL as well as the software side of things look in order to achieve this. The basic smart timer doesn't change very much. We still have our control register, status, period and duty. So this is more or less exactly the same, right? We just need to sort of pay attention to this wrap bit which is there in our status register. That's the one which is going to get connected as our IRQ. And if we think about it, right, this is just sort of a brief outline of how it might get implemented, right? You can actually look at the proper RTL code. It looks a little different from this, so I've only summarized what is happening, the relevant parts as far as setting the status wrap and the IRQ are concerned over here, right. Our module, which is the smart timer, AXI light and so on, you already have seen the examples of what the smart timer with an AXI light interface looks like. Apart from the clock and reset, the rest of the signals were a bunch of handshaking signals for the AXI light bus interface. What we are saying is we will now add one new pin, right, one new output pin corresponding to the output port corresponding to this module. Now inside the logic there are a couple of things I need to do. One of them is I need to have something which detects when I am wrapping around, basically checking whether the counter becomes equal to the period, and of course the timer should be enabled in the first place. If the timer is not enabled, then it's not really a new event that's occurring, it's just that it reached that point and got stuck for some reason. Of course that shouldn't normally happen, but I would rather check, right, make sure that the timer is currently enabled when I am looking for this particular event. Alright, I will also need some kind of logic to set the wrap bit, right. Under reset condition I set the wrap equal to 0, that's easy to understand. Else, if this wrap event occurs, that is to say the counter becomes equal to the period, I set the status wrap equal to 1. And this is what I mean by a sticky bit, because you can see in the rest of this logic, once I set it equal to 1, it's going to remain 1. It doesn't automatically become 0 unless this next condition gets satisfied. And that condition is I should write 1 into the actual W data of 0 corresponding to the status write, and the status write is going to be some kind of a short form which says am I writing into the status register. So I check whether I am writing into the status register, and bit 0 of whatever I am writing should have the value 1. Once both of these conditions are satisfied, I can say that I will reset and make status wrap equal to 0, right. So if you look at this part of it carefully, you will see that whenever the wrap event occurs, the status wrap gets set equal to 1 and it is sticky, it remains that way until I explicitly write from the software and clear it, okay. So the status wrap is one small piece of logic which is going to be there inside my RTL, which holds whether the wrap event has occurred. and I can just take that signal and feed it out as my IRQ out as well, because it satisfies all the conditions that I needed, right? It is level triggered, in other words, once it goes high it will remain high. It can be software cleared, I can write into the status register and basically clear the IRQ, and until I clear the IRQ out will remain high. Okay. So it has all the sort of behavioral characteristics that I expect from an IRQ type signal. So I am going to use this simple logic in order to actually implement the IRQ for our smart timer. Okay, so before we get into the demo with Renode, right, I just want to also very briefly show you what kind of extra information we need to provide to our Renode emulator to set things up, right. Now you might have already seen the REPL files that were used in the previous examples, right. Of course, most of them actually just point to the zinc 7000.REPL, the platform file. If you go look in that file, you will notice a couple of things. One is that of course the CPU itself is defined, right, it has an ARM v7A connected to the system bus, the type of this. It also has a line over there where it basically says it has a generic interrupt controller, which is GIC. And this GIC is also defined somewhere else in that same REPL file. It tells you that this is IRQ controllers.arm generic interrupt controller. Now what is all this? Remember that Renode itself is a package that is written in the C# programming language, it does not really matter to us. This notation, this IRQ controllers etc. is telling us which particular module in the Renode package, that is all in the software that has been used to create Renode, I should use in order to emulate the behavior of the interrupt controller, right. So in other words, the people who created Renode have constructed a model of the ARM generic interrupt controller in software and have provided that to us as a package, right. So we are not at any point in Renode directly running RTL corresponding to a GIC or to the ARM processor, it is all being emulated, right, through software. So the GIC itself contains this information saying that this is the type of interrupt controller, it is connected on the sys bus and it is basically connected at it has this particular addresses, this is the distributor, this is the CPU interface and so on, right, the GICD and the GICC, right. So all of these in other words basically tell us how to connect this particular thing to the CPU. Now as far as we are concerned, the smart timer is the one that we are creating. It's going to be a co-simulated peripheral because after all we are going to be writing Verilog code and getting it connected to the system. We give it the address and the address range as before. We also give it some frequency, some sufficiently small value so that the simulation runs reasonably fast. And then there are these two extra lines that were not there earlier, right. So what are these two lines? The first one is this piece of information which says co-simulation, which is the RTL code, to Renode. In other words, we have a co-simulated RTL code and we want to map certain signals of that into Renode. And we are saying that there is one extra output which is not the AXI bus, right, which needs to get mapped into the Renode signals, right, because as such otherwise if I think about it, IRQ out does not really have any physical meaning as far as Renode is concerned, right, it is not a well known name. The other things like the S_AXI and so on are part of the AXI bus and therefore Renode can actually recognize and automatically infer everything that is required for that bus. Over here the IRQ out, I need to specifically give some way by which Renode can recognize it as a signal which should then be connected to some other place. So I have this extra line over here just to indicate that there is one particular signal, one extra signal that needs to get mapped as part of the IRQ. And what we say is that signal, the signal number 0 of what we have over here, gets connected to the GIC at pin location or rather at interrupt location number 33, right. And as we saw earlier, we want it to actually be on the SPI, the shared peripheral interface, which means that it will actually get connected to the input number 65 of the GIC, right. So that computation is performed internally, Renode handles that automatically for us. So that is basically what we need to specify, right. Okay, one last thing, we will also in this case I will be showing a very simple part of the Linux driver. In fact, I will not really be going into any detail at all as far as that is concerned. The only thing I will show is that it will respond to an IRQ by basically keeping track of the number of IRQs it has received so far and just printing that out on the screen. It's not actually going to do any useful work with it, right? All that is a much more complicated set of functionality, right? So we will not be doing that at this point. Okay, so now let's move on to the demo.